Okay, if you've been keeping up with the homework we've covered in class thus far, you have probably completed homework 3A, problems 1 through 11. I'd just like to take some time to review your work on those problems before you move forward based on today's new material. So go ahead and grab homework 3A and let's just compare problems 1 through 11, your work done thus far. So to dive on in, the first 5 problems in this homework are all about solving. And we've done a couple examples quite similar to these in class, so of course feel free to use those as a reference. But we begin by solving cosecant squared of 3. Cosecant squared of theta equals to 3. And right away we turn cosecant into sine squared, and we take the reciprocal of the right-hand side. So using the reciprocal identity right away, it allowed us to be solving with sine, which is more familiar to us than cosecant. Since we've got a sine squared, we square root both sides to get sine alone. That gives us plus or minus the square root of 1/3. Now, as we're solving on problems 1 through 5, we do want to find exact solutions, meaning we're not going to have rounded decimals, and we want to make sure our solutions fall on the interval between 0 and 2 pi. So basically one full pass through the unit circle. So if we're told that we're looking now for where sine of theta is equal to plus or minus the square root of 1/3, basically we should be thinking about the fact that the sine value would equal to positive square root 1/3 in quadrants 1 and also in quadrant 2. And that's because the sine value corresponds to the y value, and the y value is positive in those two quadrants. However, sine of theta also equals the negative square root of 1/3, so we should have a quadrant 3 solution where the y value is negative, and also a quadrant 4 solution. So basically, if we take the inverse sine of the square root of 1/3, that will generate our quadrant 1 solution. So you can see our first solution here is a quadrant 1 answer. Then we can use our knowledge of reference angles to generate the other 3 quadrants. So for example, in quadrant 2, we need to subtract sine inverse of the square root of 1/3 from pi. So that's our second solution, giving us a quadrant 2 answer. To generate our quadrant 3 solution, we are going to take pi plus the sine inverse of 1/3. And last but not least, to get our quadrant 4 answer, this is where it looks like we've got to take 2 pi minus the sine inverse of the square root of 1/3. So we end up with 4 total solutions in this example. This is very similar to one of the class examples we did a few weeks ago, but we end up with 4 total solutions. This first problem can be a little challenging because the solutions aren't coming from special angles. We'll contrast that in just a moment with problem 2. So hopefully you found those 4 solutions for problem number 1. If we look now at problem number 2, there we go. Let's see if we can look at problem number 2. This one has cosine squared of theta equaling to 1/4. Similar to problem number 1, we begin by square rooting both sides to free up cosine. So the square root of cosine squared gives us just cosine. The square root of 1/4, remember, can be thought of as square rooting the top and the bottom separately. And we know the square root of 1 is just 1, the square root of 4 is just 2, so that's why we get back plus or minus 1/2. Now, this is going to be a special angle, so if I think about the coordinate plane for this one, we're looking on where on the unit circle would the x-coordinate be either plus or minus the square root of 1/2. One location would be in quadrant 1 at an angle of pi over 3. So our first solution here is a quadrant 1 solution. In quadrant 2 at 2 pi over 3, we'll be getting back an x-coordinate of negative 1/2, so that works as well. So our second solution here comes from quadrant 2. Another location where the x-coordinate is plus or minus 1/2 is in quadrant 3 at an angle of 4 pi over 3. So on your unit circle at 4 pi over 3, the x-coordinate should be negative 1/2. So 4 pi over 3 is our quadrant 3 solution. Last but not least, in quadrant 4, at an angle of 5 pi over 3, the x-coordinate is positive 1/2, so that satisfies what we're looking for here. So same as problem number 1, problem number 2 does have 4 solutions because of the plus or minus. These solutions are a bit more friendly, I would say, than problem number 1 because they come right from the unit circle. They come from our special angles. So hopefully those two went pretty well for you all. Let's go ahead and keep rolling. As needed, you can refer back to this video to check your work on homework. The next couple problems are a continuation of solving. So problem 3 had asked us to solve 2 sine of theta equals negative 1. We can tell a good first algebra step to isolate sine would be to divide both sides by 2. That told us sine of theta is equal to negative 1/2. And now, thinking of the unit circle, we need to be careful because it's only looking for where the y-coordinate, since it's sine, is equal to negative 1/2. So we know sine as the y value would be positive in quadrants 1 and 2. So we're not going to focus our attention there. But instead we're going to focus on a quadrant 3 angle and a quadrant 4 angle. In quadrant 3 at 7 pi over 6, the y value is negative 1/2. So that's our first solution for this problem, quadrant 3. And our second angle in quadrant 4, because sine is also negative in quadrant 4, would involve the angle of 11 pi over 6. Again, verify on your unit circle that at 11 pi over 6, the y-coordinate is equal to negative 1/2. So the two solutions for problem number 3 will be theta equals 7 pi over 6 and theta equals 11 pi over 6. The next problem, problem number 4, is very similar to one we've done in class. You'll notice right out the gates we're going to use a negative angle identity on problem number 4. So what I mean by that is when we see sine of negative theta, using the negative angle identities from our identities handout, we can state that that's equivalent to negative sine of theta, and you'll see that occurring from line 1 to line 2. Then from there to work on solving this one, factoring out the greatest common factor works well. The reason that works really nicely is if I were to build a comparable algebra equation, it would feel something like xy minus y equals 0. So I notice in this example the y-coordinate is the common factor, or the y value, and I would just be able to factor it out and solve what remains. In the same way, when we factor out sine in this equation, we're left with tangent theta minus 1. Setting sine of theta equal to 0 asks me to look for 2 places really on the unit circle where the y value is 0. That will occur at 0 radians and again at pi radians. Because we're solving on the interval between 0 and 2 pi, where 0 is included and 2 pi is not, 0 and pi are the only solutions for this side of the equation. Let's go to the other part. When we look at tangent of theta minus 1 equaling 0, that really turns into finding where on the unit circle will the tangent value be 1. And that's going to happen 2 places. The first place will be in quadrant 1 at pi over 4 radians. The second location where tangent would equal 1 is in quadrant 3 at 5 pi over 4 radians. So for problem number 4, there are a total of 4 solutions, and those are the angles 0, pi, pi over 4, and 5 pi over 4. Problem number 5 was actually done in class together, so I won't spend too much time on this one, but just to refresh you on our process, we did a very similar thing to what we just did in the last problem, which was we considered the comparable algebraic equation. So 9 sine theta minus 2 equaling 4 sine squared theta can be compared to 9x minus 2 equals 4x squared. This is just a quadratic equation. So if we set this quadratic equation equal to 0, we can factor, if it does factor, Or, of course, things like the quadratic formula are also available to us. Since we did this in class, I'm not going to break down all the steps, but I like to factor when things factor, and by a little bit of trial and error, it looks like factoring does work. So algebraically, we would have found either x is a quarter or x is 2. In our trigonometric equation, that means either sine of theta is a quarter or sine of theta is 2. We know that the sine value would be positive in quadrants 1 and 2. So we get two answers. One is just sine inverse of a quarter. That would be the quadrant 1 solution. And then to get the quadrant 2 solution, we take pi and subtract that original solution. So 2 solutions coming from that part of the equation. And then the sine of theta equals 2 part of the equation won't have any solutions. An easy way to remember that is the sine graph has a range of -1 to 1. So the graph never goes higher than 1 for the basic sine curve. So that's it for solving. Again, you've probably done a lot of good work already on these problems, so we'll go ahead and move into the next set, 6 and 7, which have a different direction. So problems 6 and 7 just ask us to simplify. For problem 6, we have secant times cosine plus cosine minus 1 over secant. And basically I hit this one with reciprocal identities. So the reciprocal identities that I utilized were the ones that state that secant is the same as 1 over cosine, and 1 over secant is the same as cosine. So taking a little bit of time to rewrite this, secant became 1 over cosine. I left cosine alone. That's a good technique often to leave cosines, change everything else besides cosines and sines. I left this next cosine term alone, and 1 over secant, I used the reciprocal identity already mentioned. These problems can feel a little vague because there's not really a clear end goal. We're just trying to rewrite it. But at the second line, we'll notice that these cosine terms cancel, leaving just a 1 for this first piece. And then the next two cosine terms are same but opposite, so they cancel out. So problem number 6 simplifies to just 1. For problem number 7, now we're in a situation where a good first step would probably be to pull out a common factor. So we have sine cubed plus cosine squared times sine. And if we factor a sine term out, that will leave us with sine squared plus cosine squared. Sine squared plus cosine squared should feel like a familiar identity for us. That's called the Pythagorean identity. And that's one of the kind of the classic Pythagorean identity. There are 3 different forms, but the sine squared plus cosine squared equaling 1 is probably the most popular. So we went ahead and replaced sine squared plus cosine squared with 1. And then sine of theta times 1 is just sine of theta. So problem 6 and 7 really allowed us to utilize our knowledge of identities with just the goal of rewriting. And that will help us when we actually get to verifying. So it looks like problems 8 and 9 are now actually asking us to verify. This is where we'd like to keep one side of the equation the same the whole way down and manipulate the other. Typically we choose the side that feels more complicated and we rewrite that carefully. You may or may not agree, but I went ahead and chose the right-hand side as the side that felt more complicated. What I've done so far is I've brought cosine squared in the denominator up to the numerator as a secant squared. So I'm just utilizing basically that reciprocal identity we've already mentioned today. At the same time, I went ahead and FOILed in the numerator, so I multiplied 1 times 1, 1 times cosine squared, negative cosine squared times 1, and negative cosine squared times cosine squared. That generated 1 minus cosine to the 4th. The whole way down I'm keeping the left-hand side the same, so that's why I'm just rewriting same for the left-hand side. So just writing same the whole way down because we're not changing that left-hand side. So on the right-hand side, the next step I took was just to distribute secant squared to the parentheses. that gave secant squared minus secant squared cosine to the fourth. But secant squared cosine to the fourth does simplify because secant squared is really the same as 1 over cosine squared. We had already talked about that earlier. So timesing by cosine to the fourth really reduces two of those cosine terms. So that's how secant squared theta cosine to the fourth theta becomes simply cosine squared theta. At every stage of verifying, it helps to look back at the side you're trying to match to. So at this stage of the game, I'm noticing that secant looks good in terms of the original left-hand side. So that helps me know that it's the cosine squared term I should try to rewrite. Using a Pythagorean identity, cosine squared is the same as 1 minus sine squared. We've used that Pythagorean identity quite a bit. And then this last step of just distributing the negative through gives us sine squared, really plus secant squared minus 1, and now that's identical to the left-hand side. So problem number 8 is now verified. Your process could look a little different, but as long as each step you've taken is following either an identity or an algebra step, you should be good to go. 9 is also verified, so this will feel similar. I'll just real quick go through the identities I chose to use. I rewrote tangent cubed as sine cubed over cosine cubed through a quotient identity. Then I rewrote cosecant squared theta as 1 over sine squared theta using a reciprocal identity. Then I rewrote cotangent squared as cosine squared over sine squared, and I left the cosine and sine the same. If you're doing number 9 and not quite sure where to start, I think most folks would agree the left-hand side is more complicated. And because there's so much going on the left-hand side, my basic process was to rewrite everything in terms of sines and cosines. That seemed to make it feel a little bit more understandable. When I multiplied all across the numerator and denominator, I got sine to the fourth theta times cosine cubed of theta on top and bottom. And that means we really just have a fancy form of 1, which is what the right-hand side was equal to. So that one is verified as well. The last two problems are going to come from the sum and difference identities, so we'll take a look at those next. Problem number 10 was actually done in class a couple times, both during lecture and then on the exit slip. So I'm not going to spend too much time in this video reviewing that problem since we've done it twice now. But hopefully you got an answer of either square root 2 plus square root 6 over square root 2 minus square root 6. That's probably what most of us got. You may have also gotten an equivalent answer of 1 plus square root 3 over 1 minus square root 3, or perhaps even negative 2 minus square root 3. So any of those three answers are fine. My guess is the majority of us found the first solution I mentioned. As a quick check on these, you can always type the left-hand side into your calculator as long as you're in degree mode. Get a decimal approximation. Type in your solution in exact form, and the decimals should be about the same. They could be off a little due to rounding. So that's one quick way to check those. And then last but certainly not least, problem 11 is another sum and difference identity. When we're working with sum and difference identities, it means we're beginning with a problem that involves an angle that's not on the unit circle. So 25 pi over 12 is not what we would call a special angle. The denominator of 12 is not something we've worked a lot with. But we can take 25 pi over 12 and break it down into two familiar angles. There are multiple correct ways to do this. I'll just share what I happen to do in this problem. I took 25 and broke it as 10 plus 15. And the reason I went ahead and did it that way is if I reduce these fractions down, I'll get angles that look familiar to me. So 10 pi over 12 would reduce to 5 pi over 6. That is a unit circle angle, so that's a good thing. 15 pi over 12 looks like it would reduce to, that would be 5 pi over 4. That's also a familiar angle from the unit circle. So again, you've likely went through this whole process already. So just comparing end results carefully, we should have arrived at radical 6 plus radical 2 all over 4. And if you type in cosine of 25 pi over 12 in a calculator, and get the decimal approximation, and then type square root 6 plus square root 2 over 4 in a calculator and get that decimal approximation, they should be basically the same. So I do encourage you to check your work in that way. So hopefully problems 1 through 11 have gone well in the homework, and then after today there's a couple new ones you'll be able to try, which I'll mention in just a moment.